Welcome back to ECE 441A, 541A. As a reminder, your first exam is next Friday. It's in a week. And so I'm guessing that the classroom will be a little bit fuller in a week, so make sure and get here on time. Hopefully we will have enough chairs. There's quite a few actually in the class. Homework 2 is due on the 21st, which is the Wednesday preceding the exam day, and we'll do a little bit maybe on one of the last homework assignments in terms of a hint or help during today's class. Lab number 1 is you need to turn it in to the Dropbox by the 3rd of October, but I really would recommend that you understand the concepts going into exam number 1. Topics or that particular idea will be a part of exam number 1. Today what I want to do is finish up first order systems. I will list or discuss some common first order systems just to get you aware of where these might arise. Then we will go ahead and return to what we had started last time and complete our first order system identification example. Then we'll do it with a little bit different data. Under a little bit different circumstances, we'll examine how we might identify a first order system, and that actually is connected with one of your homework problems. And then we will start talking about second order systems, which is really lab number 1, and you already have additional material for lab number 1. You have a video to watch and some notes and then some pre-lab and obviously the lab itself. But we'll try to connect up a little bit with that in terms of second order system identification. That's what the ID means in the classroom in addition to what's on D2L. If I suggest or say something about a first order system, if you have an electrical engineering background, I'm thinking you might immediately think of this particular RC network or this RC system. And in this case, we're dealing with ICE. ICE, where we know that the current through that capacitor is equal to C times the time rate of change of the voltage across that capacitor. Using that and performing KVL around that single mesh, we then can write our governing differential equation. We have going from the bottom lower left corner of that circuit minus V sub I. Then we have the voltage dropped across the resistor, which is R times I, but remember I is C V naught prime. So RC V naught prime is the voltage dropped across the resistor, and then we just have the voltage across that capacitor V naught. If you now isolate for that derivative term in that expression, you will have this first order differential equation. And in this particular case, if I ask you for the system matrix or the A matrix, what would that be equal to? Are you starting to see the state space representation falling out of these systems? It's simply this minus 1 over RC. That's our A matrix. It's a scalar, it's a 1 by 1 matrix, but it is an A matrix, where our state vector is V naught, our input is V sub I, and so we have x prime equal AX plus BU. The input matrix B is this scaling of our input. In this example, that's 1 over RC. We could find a transfer function, and when we're dealing with transfer functions, what happens to the initial conditions? We don't worry about them because we're really just looking at behavior, dynamic behavior. We're not trying to solve or create a solution. When we want a solution, then we need to consider all the pieces that make up that solution, and the initial condition could be one of those pieces, as is the forcing terms that are exciting that system. If we Laplace transform that governing differential equation, Then we have S, replacing the derivative operation in the time domain. V naught, and these RCs are constant. The V naught simply becomes capital V naught of S, and the V sub I becomes capital V sub I. We can collect terms containing the V naught and start dividing things around or moving things around so that we have our transfer function, which is the ratio of our output Laplace transform over the input Laplace transform. That becomes 1 over RC over S plus 1 over RC. And that's a first order system. You can see that because you now have a polynomial in the denominator of first order. And where's our pole located? It's the value of S that causes that denominator to vanish, or the values of S. In this case, it's one value, and that value of S that causes the denominator to vanish is minus 1 over RC. Is this RC circuit stable? Yes, you would have expected that, right? It's a passive system with an energy storage device in the form of a capacitor, but now you have this, and it's a low-pass filter, and you can control the pole of that low-pass filter by the values that you pick for R and C. You can, this first transfer function on just to the right of the V naught over VI, that's in what we call pole zero form. It explicitly identifies the zeros and the poles as factors. If we factor out the pole and normalize the constant in our polynomial factors, then we have it in time constant form, and in this case we have 1 over tau s plus 1. And what's the time constant? RC. And that's related in what way to the pole? It's the reciprocal, isn't it? The pole was at minus 1 over RC. The time constant is RC. So the pole is at minus 1 over tau. That's if you have a, I know artistic talent maybe is a little lacking, but now another first order system is this high-powered vehicle or a cruise control, where if you wanted to, you could look at how to maybe more effectively understand what's going on here, but you know how to deal with this. If we simply look at this vehicle having some kind of damping, maybe it's the road friction and the air surrounding it, the damping is proportional to the velocity of the vehicle. We now have a force that's opposing the forward force trying to drive that car forward. The free body diagram then has these three pieces: the inertial force, the force due to the damping, and the propulsion force U. And you can write that equation or find the equilibrium condition, which is just what forces are going left, those must equal the forces going right, or the algebraic sum of those forces is equal to 0. And in this case, we have m times the velocity's derivative, which is acceleration, ma, plus bv equaling the force moving that car forward. And I hope you see that that's a first order equation. We've now seen a first order equation in electrical terms and mechanical terms. And in this case, if we do the Laplace transform, all of this you should almost be doing in your sleep at this point. You should be able to wake up, roll over, and just on a piece of paper start writing these equations. If somebody says, if you wake up and you go, oh, first order, you can immediately write down a first order differential equation. Then you'll be able to transfer that, or find the transfer function by doing the Laplace transform. And in this case, look at what falls out: alpha over tau s plus 1. And the only difference between this first order system and the RC circuit was now our numerator coefficient is a little different, so our scaling is different. But it's still a first order transfer function or a first order system, a mechanical system, and you could control this to give you the speed that you need so that you don't violate the law. Design a cruise control for this so that you have a nice, effective behavior. You can do this for a thermal system. Maybe we could model this room, its temperature, and now we have an input, a step input. If we all came in at the same time, we are basically 100-watt light bulbs. We now have 60 of those here. That generates quite a bit of heat, and we could measure the temperature increase in this room, and it would exhibit a first order behavior. And now when I say first order, you might think, oh, that pole's in the left half plane. Oh, I can see the time response, this exponential behavior. Maybe we have fluid in a tank, and its fluid is either going up or down depending on whether we've punched a hole in it and didn't try to put a hose to refill the fluid in the tank, or maybe we're just letting it fill up with a hose. That also has this first order dynamic behavior to it. If, and this is related to one of your homework problems, the DC motor that we talked about, I don't even know how long ago that was, but I do have the date, the 9th of September, that seems like quite a while ago, but it wasn't that long ago. If you look at that at the end, and I think I put these in after class, so you'll have to look at the tail end of those notes, but you can show that if omega is the velocity of that spinning shaft on the DC motor, you can find the transfer function between the applied voltage of that armature-controlled DC motor and the shaft's rotation. But now it's in all these crazy coefficients. K sub m was the motor constant, R sub a was the resistance of the armature circuit, J was the rotational inertia of the motor shaft, and B was the damping of that DC motor. What's the order of that system? First, we only have one S in the denominator, even though we have all these coefficients, and we can show that. If we multiply that R sub a, that resistance across, if we factor out all the constants so that our constant coefficient is 1, now whatever is scaling S is our time constant. Maybe it's a mess, but maybe we don't need to know that. Maybe we just want to know how to model this circuit as a first order transfer function, and I'm hoping you can see that what I've circled, all of that combined is just a constant, and we could call that alpha. Everything scaling the S is just a tau. So that now we again have this alpha over tau S plus 1 as our model for a first order DC motor's dynamics. And it's first order because we're only concerned with the transfer function between the applied voltage and the rotational velocity of the shaft, not the angle of the shaft, but how fast it's spinning. Again, we have this first order transfer function. That should get you thinking about a lot of different environments where a first order dynamic behavior results or occurs. And we will be wanting to maybe change those dynamics or modify those, but first we have to identify those. And in terms of identifying a first order transfer function, how many unknown coefficients are in that transfer function? 2. Alpha, which is the DC gain, and tau, which is the time constant. If you can find the time constant and the DC gain of a first order system, you have a transfer function description of that system, whether it's a thermal system, whether it's an electrical system, whether it's a mechanical system. You now have a way of describing it in the form of a transfer function. And that's what we had started with last time. We have a first order system and we want to identify it. system identification, and we're assuming that we're applying a step or a constant input to that system. The input u is going to be some constant as a function of time. We want to apply that constant, and when we do, what happens to the output? It has this first order exponential shape. And how much of that we have available to us or no depends on the problem. But if we were using a 1% settling time, what do we mean by settling time? This needs to be clear, so if somebody starts talking about settling time, what are they referring to? Okay, it's the time taken, maybe not to reach the steady state, because we may never reach it, because then they would say, oh, that's never going to happen. So how can I find my settling time? Well, we make it such that we're within a tube of where we are headed. A 1% tube, a 2% tube. If it's 1%, then we're much closer. If it's 2%, we're not that much farther away, but it's a 2% tube that we try to get into and stay in, and that's when we say there's our settling time. Our 1% settling time is now we're within 1% of where we eventually will end up. If it's a 1% settling time, that's really looking at e to the minus 5. Does anyone have that memorized? E to the minus 5. How big is that? It's very small, isn't it? It's less than 0.01. That's where the 1% comes, but it's pretty close to 0.01. So e to the minus 5, that's 5 time constants. If you looked at, a lot of times you'll see some formula that's e to the minus t over tau. If you replace t with 5 time constants, that's where this e to the minus 5 comes from. The taus cancel, and you're left with e to the minus 5, which is a little bit less than 0.01, but that's our 1% settling time. And we can also measure the final value that we approach, and we've been calling that a sub 1. Now we're returning to what we had started with last time. We want to identify capital G of S, our transfer function for a first order system. And we are assuming that the input that we're using or applying to this system is a constant. We're assuming that that's A, which in the frequency domain says that its Laplace transformed formula is A over S. You Laplace transform a constant, it's now that constant over S. In this expression, then, we have all of the parameterized variables or expressions that we need are G, alpha over tau S plus 1. And I hope you now feel comfortable that that can occur from many different systems. And our U, capital U of S, is A over S. What are we trying to do? We're trying to find alpha and tau. And it may be that somebody tells us or gives us this exponential curve. And if they do, then we can immediately identify when do we finally reach 1% of our final value. And a lot of times that's just an eyeball, but that's close enough. You can just say, oh, I'm going to draw my line here and call that capital T sub S. That's now 5 time constants, or 5 tau. And you can measure the final value that you reach, which is what we're labeling as A sub 1. And this, everyone remembered. I was so proud. Everyone remembered the final value theorem last time, right? Yes. If you didn't, you went home and you studied it up, and now you definitely know it. But that tells you, in the time domain, as you reach your final value, in this case, the limit as t goes to infinity on y of t, We can find that by looking at the frequency domain version of capital Y of S, and that's the limit as S goes to 0 of S Y of S. What do we know in this final value expression if somebody gives you that picture above? You know the left-hand side, right? You know the final value of your output if somebody gives you that or if you measure it experimentally. You now know what you have for a final value. If we plug in or substitute the formulas that we know, alpha over tau s plus 1, the u is a over s, and we replace that in the limit as s goes to 0 of sy of s, the s's cancel. We let s go to 0 in the denominator, and the denominator is well behaved. We end up with a 1, and all that remains is a alpha. We know what A is. Maybe we've said we put in 4 volts. So capital A would be 4. If we put in 10 volts, capital A would be 10. A1 was our final value of the output. We can measure that. So now this gives us a way of identifying the alpha. And what did we say the alpha was in our system? The DC gain. That's the gain that that system will have at a frequency of 0. Or if you put in a constant, then that constant will be scaled by that DC gain alpha. We put in an A, it's scaled by alpha, and that gives us or takes us to our final value of A1. Now what? We use our settling time to find the other unknown constant. We can say our settling time, 1%, is T sub s, but we now know that that's simply 5 tau. And we could, it's not equal, we could say is approximately 5 tau, but this, we can measure T sub s, we can identify that from our data. When do we finally get close enough within 1% of our final value? Boom, that's T sub s. We can now solve that for tau. And we've now identified our system. We now can write down, with that experimental information, we now have our first order system described or modeled. What if we now have a homework problem that presents us with a little different pieces of information? Let's examine this first order system ID more generally. In your homework, you're talking about a DC motor, and you could go back and you could find that, and in the notes you could find all these R sub A's, the J's, the B's, the K sub M's, but at the end of the day, we could say, oh, the transfer function between the voltage applied at the armature of that DC motor and the motor's shaft is just a first order transfer function. And I can now model that as alpha over tau s plus 1. This is now our G of s, which is a first order transfer function. What's our objective? We're just trying to find alpha and tau, just like before. But now maybe somebody gives us different information than that entire curve or the final value and the settling time. Maybe they give us something a little differently. But we can solve this relationship. We can now say that omega sub s is our transfer function g of s times our input Laplace transform v of s. And let's just assume that somebody's applying a constant voltage to the input of our system, and let's say that that constant is A. We can now inverse Laplace transform that to find little omega t. Omega t is the inverse Laplace transform of omega of s, which is the inverse Laplace transform of g of s. G was alpha over tau s plus 1 times u, which was as. And can you inverse Laplace transform that? Well, maybe that's in a different form than you're used to taking into the time domain. This is in time constant form because we have our constant coefficient normalized to 1. That's time constant form. We can rewrite that in pole zero form. Suppose I now factor out the tau in the denominator. Or if that still doesn't look right because of that tau sitting down there, let's just pull that upstairs so that we now have A alpha over tau s plus 1 over tau. This now, I hope, makes you feel a little bit more warm and fuzzy. This is now in pole zero form. And you might be able to, if you don't have your table, Laplace transform table memorized, you might be able to see something like this in your Laplace transform tables, or at least you can now think about these pole factors in the denominator. Now, if we wanted to do this step by step, what process or what procedure would we employ to obtain the inverse Laplace transform? Partial fraction expansion. And how many terms do I have in my partial fraction expansion? Let's move up in the alphabet. Let's use some B's. So we're jumping up there pretty high now. Now you can go home and tell your parents you did your A's and B's today. Earlier in the semester, we were doing A, B, C, D, weren't we? We've had to regress. We're just back to the B. But we now have B1 over S, and what's the other one? Does that look familiar? That's our partial fraction expansion. If we could find B1 and B2, we could immediately write down our time domain expression for omega sub t, or omega of t. How do we find B1? We multiply by its denominator factor every term, which is s, and we let that factor vanish, or we set s equal to the value that will cause that to disappear. And in this case, it's easy. That's s equals 0. If we multiply everything by s and let s equal to 0, the b2 factor goes away because we've annihilated that by setting s equal to 0. What happens on the left-hand side? The a alpha over tau, we've multiplied by s, so that s gets canceled, and we let the other factor, its relationship, we put s equal to 0. So that we now have a alpha over tau. Downstairs, we just have 1 over tau, and that's actually equal to b1. And if that looks a little odd because it's a ratio of ratios, luckily the denominator of those two factors is the same. It's tau. And we can now say that b sub 1 in that partial fraction expansion is just our applied constant, a, times the DC gain of our system, a alpha. So b1 is a alpha. What about b sub 2? We can do the same strategy. We can multiply by the factor s plus 1 over tau on every term and let s equal the value that forces that term to go to 0. Or we let s equal to minus 1 over tau. And that now isolates b2. It gets rid of the b1 piece, and our left piece is now a alpha over tau all over. We've canceled the s plus 1 over tau because we multiplied by it, but now we're left with s. But what did we say we're replacing s with? Minus 1 over tau. And that's equal to b sub 2. So that now b sub 2, if we do the simplification, now becomes the negative of b1, or minus a alpha. And we're essentially finished in terms of what our time domain expression will be for our shaft velocity, omega t. That's the inverse Laplace transform of b1 over s, which is, if we take that into the time domain, what's b1 over s become? It's a Friday. I can go home and relax maybe later tonight. Maybe. Oh my goodness. They really remembered their 320 material. What's b1 over s in the time domain? b1. I'm going to have to turn this into a cheer, get something, get you going. This is just b1, isn't it? And what's the other piece? If we inverse Laplace transform b2 over s plus 1 over tau, yes, yes. So this is, I'll just say it if I didn't even hear it right, but they'll never know. It's not going to get picked up on the microphone. But this is now b sub 2 e to the minus t over tau. Or we now know what A1 or B1 and B2 are in terms of the parameterized values in our expression for the system G and the applied input. They're just combinations of A and alpha. We can factor that out, and we now have A alpha 1 minus e to the minus t over tau. I think I'm finished. I hate to even continue after that last stellar performance on the inverse Laplace transform of b1 over s. But now what? Now what do we do? What are we trying to do? We're trying to find alpha and tau, aren't we? from maybe measured data. We're still looking for alpha and tau. So we're still looking at, well, we're looking at a lot of things, but we're looking for alpha and tau. And if you're in a job interview and somebody goes, oh, can you identify a first order system? And career fairs next week, so you have the weekend to learn everything that you've forgotten in your first 4 years, 3 years, whatever it's been. But if they say first order system identification, what would you do? Buy time, right? You would take out your wallet and buy some time, but you would do that by sketching. You would say, oh, here, let me sketch what you're looking for. And you would say, oh, a first order system, and your output is omega of t. Could you now sketch a first order system? And the answer is yes, right? What's that look like? That's just this as a function of time. And you could draw it better than that. But suppose now that they throw a curveball at you and they say, I'm not going to give you that entire blue line. I'm just going to tell you that shouldn't be dipping, so maybe I'll redraw that. That should just be flat. Something like that. Maybe they just tell you what's out here, and maybe they say, I'm just going to tell you what the value was right at T1. I'm going to take a picture or plug in the instruments, and at time T1, I'm going to tell you how fast that shaft was moving. And then I've fallen asleep, and I'm going to wake up, and, oh, here it's at steady state. This is where it's finally at. Here's my final value for the shaft velocity. So you're not continually collecting data. You're now given this, which is, let's say, omega final value. You know what T1 is, and you're going, oh, shoot, Tharp only told us how to do this when we have a settling time. When we had this given, we were maybe saying, oh, here's T sub s, and I know that that's 5 tau, and now we haven't been given this. This was our T sub s. And now we don't know that. And maybe I'll put a disclaimer here. This is a 1% settling time. And I know that you are very faithfully reading the textbook and following along and reading ahead. And so you've probably said, I don't remember 5 tau. Well, the textbook likes to use a 2% settling time, which is 4 tau. So that's the note that I'm wanting to, here's the disclaimer. The textbook usually uses 2% settling time. And there, T sub s is 4 tau. So that now you're looking at e to the minus 4, which is approximately 0.02. It's actually closer to something like that, I think. I keep track of all of these e's because at the end of the semester I have to use those e's. No, I don't want to use those e's very much at the end of the semester. Okay? And don't try to say that, oh, that was E. I was trying to get an E because that's 2.7. No, it's a different E. It's a capital E. Where were we going? Oh, we're still trying. We're buying time. We're buying time. We're thinking. We're trying to figure out how do I, but now maybe they've given you this time, T1, and they've told you that value, omega 1. But they did not give you the settling time. And maybe they've told you how much they excited the system with. what constant value was applied. Given constant input value, let's say, to be consistent with before A. But now you pull out of your pocket this expression. And you could rederive this, right? That could buy you more time. You could rederive this first order solution on the back of an envelope or at wherever you're at, a napkin. Maybe tonight you'll be having a napkin next to your coaster. You can start doing all this. In addition to the block diagrams that we've been using in the previous Fridays, now you can start solving first order differential equations. But we have this expression, and we're trying to find alpha and tau. What do we know? We know A, capital A, that was the constant input. And we are told a particular collection of omega 1, at a given time, t1. So we could look at this at a particular point in time. What else do we know? Maybe I didn't make it too explicit. Well, I did. I told you that, didn't I? Have arrows going everywhere. We were given omega final value. Can you find an expression for omega final value using that time domain expression for the shaft velocity or the angular rotation? Can you let t go to infinity? Yes, you're seniors and graduate students. You can let t go to infinity, can't we? So if we do that, we will find omega final value. That's now the limit as t goes to infinity of omega t, but that's the limit as t goes to infinity of that expression, a alpha 1 minus e to the minus t over tau. What happens as t gets large? The e term, the exponential, goes away, doesn't it? But we're still left with some information, hopefully. We have two terms. We have an a alpha term, and then we have an a alpha that's exponentially decaying. And that one's gone at infinity. And how long do we have to wait for infinite time? Practically 5 tau. That's not that long, is it? So infinity can be pretty quick in an electrical system. We've now said that we know this is equal to a alpha. And that's just omega sub final value, which we were also calling at one point A1. So that now we can find our alpha, one of the two unknowns in our first order differential equation, by saying that that's now A alpha is A1, and so alpha is just A1 over A. Our final value, A1 over what we applied to the system, which was A, and that gives us alpha. We've now simply, all we've used is that last tail of our expression. We want to use this other piece of information, omega 1 and T1. If we now substitute T, or replace T with T sub 1, we now have omega 1, and that was given. They told us what the shaft velocity was at T1. They said that's omega 1. And that's now equal to A alpha times 1 minus e to the minus. Now we have T1 over tau. What do we have? This was given, as was T1. This A was known. and we just calculated alpha. Are you now feeling a little bit more comfortable in this job interview? What do we know now? We know everything but one unknown. We have everything else available to us. We can now use this star to solve for tau. And you can do that, right? Please? You can divide things out, you know, A and alpha. You can subtract. You now have an exponential. You can take the natural log. You can get rid of that e to the something, and now you have a minus t over tau equaling a natural log of something. And you can solve for that. So you've now found tau. Questions on that? That means we're ready for doubling the fun. We're now going into second order system identification. And before we jump headfirst into this, why don't we do a little bit of a review since we were so successful with that earlier. What if I now said, can you inverse Laplace transform the following? First, let me correct that curly bracket. Omega d over s plus sigma squared plus omega sub d squared. Where this whole thing, we could say, is y sub a of s. And we want to know, what is that? So you satisfied your interviewer with your stellar performance on first order system identification when they even threw you a curve and gave you T1 and omega 1. Now they said, well, let's look at this a little bit more. What about a second order system? And you go, oh, really? Now you don't say that. You may be thinking that, but your face is just lit up, right? It's just excitement. You're just all excited with trying to answer these questions, and now you're going, okay, second order. Is this second order, first of all? Yes, it's s squared in the denominator. What could you do to buy time while you're thinking about what's going on here? What could you tell us about this? Can you say anything about the poles and zeros? Can you sketch the S-plane plot of poles and zeros? Can you put down X's and O's? Maybe your interviewer used to play sports and they like X's and O's, and you can go, oh, let's look at some X's and O's. And the interviewer's going, all right, I'm liking this. Where do you put X's and where do you put O's? And do we have any O's, any zeros, any finite zeros in this capital Y sub A of S? No, there's no finite values of S that cause that to equal 0. Do we have any poles? And where are those poles located? For a second order transfer function, just for a second order transfer function, as long as your coefficients are positive, you know you have negative real parts. If they're both there, if they're present and positive. That's how I like to think about it. They're present and positive. And they are. They're present and positive, but in this factored form, they should be jumping out at us. There's the real part, minus a, and the imaginary part is plus and minus omega d. So we have poles at minus a, plus and minus j omega sub d. Those are our poles, no zeros. And what does this look like in terms of time domain response? Question?
Is that S plus A or S plus sigma?
Thank you. It's both, apparently. That was a sigma. If I had sigma up in my transfer function. I wondered why you guys were giving me this questioning look, but it's minus sigma. What does this look like? This is an exponentially damped sinusoid, and I want you to go home and start reviewing your second order inverse Laplace and Laplace transform so that we're very comfortable with these exponentially damped sines and cosines, and we'll pick up at that point on Monday.
This is Mark.